chapters 6, 7, and 8. So we'll do the same this quarter. The reason is this needs to be a 12 lecture class in order for it to count as 5 units. So we do have to make that day up. But again, it'll be an optional practice problem day. When I have the date and room, I'll let you all know when that is. Questions about that? Okay. Obviously, the midterm is next week, same time and place as our regular class. So let's get started with our midterm review then. So the very first thing we learned, well, actually, let me take a step back again. Let me talk about the midterm itself. So the midterm is 28 multiple choice questions, all multiple choice. You get one sheet of notes. They can be typed or handwritten. You can use both sides. You'll get the full 3 hours for the test. It is certainly not written to be a 3-hour test, maybe about a 1-hour test. So take your time, read slow, make sure you understand the questions. Bring a calculator and a pencil. The test will be Scantron. I will bring the Scantrons, don't worry about that, but do bring a pencil. Anything I'm forgetting? Any questions you have about the exam?
How many questions was that again?
I'm sorry? 28 multiple choice.
How many points is each question worth, and do we get partial credit?
Each question is just 1 point, 1 point each, and no partial credits. It's all multiple choice, so no partial credit.
And you're supposed to give us the Scantrons?
I will bring the Scantron to us.
Regarding the homework that's going to be due, is that just going to be on chapter 5?
The homework that's due next week is chapters 4 and 5.
4 and 5.
Yeah.
So the midterm is chapters 1 through 5?
The midterm is chapters 1 through 5.
Is it a full sheet of paper or just like one cell card?
One full 8.5 by 11 sheet of paper, both sides. Yes.
Is it graded on a curve?
Is it graded on a curve? Only if it absolutely must be, which, so I used to always grade, this is a good time to talk about how I grade this class. I used to always grade on a curve, and every quarter the curve was exactly the same. We'll see in chapter 7 why. This is statistics. The curve was the same every time, so eventually I just stopped curving, and what I wrote on the syllabus, if you go look at that grade breakdown, that is the result of the curve every quarter. So instead of calling it a curve, I just made it a hard and fast. A starts at 85, and so forth, that sort of thing. Does that make sense? Other questions?
You're going to go over all the formulas that we would need to do.
Yes, today, if I write a formula on the board, write it on your cheat sheet. Anything else? All right, now let's get started with our review. So the first thing we learned way back when was the types of variables. Remember, a variable is some quantity that I'm measuring, or, well, we had numerical and categorical. So a numerical variable would be if I'm measuring your guys' height or weight or GPA or miles you commuted to get here. As it sounds, it's a number that measures some quantity. I can also measure some quality. Your hair color, your gender, car you drive, your favorite TV show, things like that. They're saying something about you, but clearly they're not numerical. We call those categorical or qualitative variables. We also saw in chapter 1, we talked about causality. We talked about the difference between an observational study and an experiment. So in an observational study, which is what it sounds like, I'm merely observing. The main point there is I am not intervening in the test subject's environment in any way. In an observational study, I cannot conclude causation. So why can I not conclude causation?
Because you don't have a experiment, control.
I don't have a controlled experiment, true.
You can't say the different reasons the result was caused because you don't know
Exactly.
what they are.
Exactly. So what I'm looking for is confounding variables, which is what you're describing. In an observational study, I cannot conclude causation because it suffers from confounding variables. A confounding variable, so the example we had was gray hair and wrinkles. We see these going hand in hand, meaning if I notice someone has gray hair, there's a higher probability that they have wrinkles. What do we call that?
Correlation.
For a numerical variable, a correlation, which is the same as an association for a categorical variable. Age is causing both of these things. So age prevents me from drawing a causal relationship one way or the other. Age is a confounding variable. Studies we've done with lung cancer and smoking, same thing. All studies with lung cancer and smoking are observational studies. We see this guy smoked for a long time and died of lung cancer. We see that happening over and over. A strong association. Some scientists have proposed genetics as a confounding variable. We certainly know genetics can play a role in whether or not you get cancer. Some have theorized it can play a role in whether or not you're going to get addicted to smoking, if that chemical replaces something in your body. Yes.
What if it was a long-term study for smoking?
Even long term, if it's not an experiment, which we can't do an experiment on smoking, that would involve telling these people go smoke for the next 30 years and let's see what happens to you when you don't smoke. So we've never done an experiment on smoking, and even if it's a long-term observational study, it's still an observational study. So I mean, this means mathematically we can't conclude cause. Right? Mathematics and reality don't always line up. If a biologist who's been studying cancer for 50 years tells you, I strongly believe smoking causes lung cancer, which you would, then don't go smoke. This is just the math right now cannot allow us to prove that cause. In an experiment, we can prove cause. So in an experiment, I can actually account for all these possible confounding variables. And how do we do that? So that's the defining characteristic of an experiment. You've intervened in the test subject's environment. But what makes it a good experiment where I can conclude a causal relationship?
When you compare a control and a treatment group?
When I have a control group and a treatment group, the key word here is randomization. As long as I split my test subjects randomly between my control and treatment group, then I've accounted for all confounding variables. So any confounding variables such as age or genetics, as long as I've randomly split my test subjects, the two groups will be the same on average. I'm testing a weight loss drug, I don't want to put like high metabolism people in one group and low in the other. If I do it randomly, on average, they'll have the same metabolism as a whole. Questions there? Then we saw a common plot for observing data, the histogram. The histogram shows us the distribution of the data, where the data occurs. The x-axis is the data values. So if this were a dice, it would have 1, 2, 3, 4, 5, 6. The y-axis is frequency, or counts. And the height of the bar tells you how often that value occurs. So if I flip a dice 1,000 times, my dice should all be the same height. So let's say I flip it 6,000 times, then this would be 1,000. The height, just how often that occurred. When we're observing data with a histogram, we can notice different shapes in our distribution. A distribution that has the bulk of its data down here, but slowly declines in this positive direction, meaning as we get to higher and higher values, they're less and less frequent. What do we call this shape? Right skewed. Remember, we named the skew in the direction of the tail. If I flip it and I have that slow decline to the left, that's a left skewed distribution.
Could you give an example of what a right skew would be in terms of like you use the dice for that one, what would be?
Right skewed, so we talked about personal wealth is the classic example of a right skewed distribution. We've all heard about the 99% versus the 1%. So as we get to higher and higher wealths, we have less and less people making that amount of money. If there's no skew, meaning the tails in each direction are pretty much the same, what do we call that?
Symmetric.
Symmetric. Symmetric just means you can cut it in half, and it's roughly the same on both sides. For our distributions, we want
If the mean is greater than the median, then it's, what was that?
that is true. If the mean is great, we're about to get to that. But what you said is true. If the mean is greater than the median, it is right skewed. We want to, when we have a distribution, we want to talk about two characteristics of it. Its center and how spread out the data is. So for center, we had two measures. What were our two measures of center of a distribution?
The unimodal, bimodal,
Unimodal and bimodal.
and
The
multi.
unimodal and bimodal describe how many peaks the distribution has. So remember, the tallest bar in a distribution is its mode. So something like this that has two peaks we'd call bimodal. But that's not measuring the center. So one example is the mean, the average. That's a one measure of the center of a distribution. What was our other measure? The mode was one that we don't really work with. What was the other one we really work with? The median. So we have the mean, x bar, which we call the mean. You just add up all your values. Let's say I have n values, and divide by n. The median let's do an example. So remember, the median, you put all your data in order, and then whichever one's the middle value is the median. So let's say I have these 7 data points. So on the midterm, I'm going to give you 7 data points because 7 works out nicely. We have a middle, and then it allows us to find Q1 and Q3 nicely. We'll do examples of that soon as well. My first step is to put it in order. I know it sounds like I'm beating a dead horse by saying that a lot, but it's the most common mistake I see. I see people just leave the list as is and then pick that one as the median because it's in the middle. So first you order it. I have 14. The middle of 7 values is going to be this 4th value here. Has 3 on each side of it. So that's my median. 45. Why do I need 2 measures of center?
They tell you different things.
Well, they're attempting to tell me the same thing, but on certain occasions one will fail.
It depends on the outliers.
The mean is incredibly susceptible to outliers. So always think about that sheep example in the lecture notes. We had a village of 10 people. 9 of them had 0 sheep each. One guy has 1,000 sheep. The mean says, on average, every person has 100 sheep. So that's really misleading. That outlier, that guy with 1,000 sheep, really boosted up that average, giving me a misleading picture. Imagine if we're all sitting here trying to figure out how much money we have on average, and then suddenly Warren Buffett walks in. He's going to really pull that average, right? The median, being just the middle value of this ordered list, doesn't change. Let's say I change this 83 to an 83,000. Certainly my mean would go way up. But did my median change at all?
No.
No. So the mean is fine when we have a symmetric distribution with no skewness to pull the mean in either direction. But if we have a skewed distribution, we definitely want to go with the median because it's not affected by those extreme values. Yes.
So when we're asked to find the center, we have to do both the equation and find the
No, I would all, if I asked you to find the center, I would either tell you which one to use, or I'd show you a picture, and let's say it looks like this, you'd know to use the median.
It will be one where there's a, for example, like for the mean, where it might be a even number.
For the
And you have
mean,
to find, yeah, we'll have to find in between the,
so that would only come up for the median. You mean if I gave you 4 numbers,
right,
so there's no middle value because it's only 4 numbers, you would just take the average of these 2. But as I just mentioned, on a test I will give you 7 numbers,
okay.
so that there will be an exact center. So you have to worry about that. Other questions there?
There, on the homework, there were examples where you had to look at the graph,
Mhm.
and then it just told you like a description of like the
The
situation.
television one?
And you had to figure out what graph it went.
Oh, that one.
Yeah, like how can you tell by looking at it?
It can be tricky. I'm not going to put, so the homework question she's referring to is there's 3 scenarios and then 3 histograms, and you have to match the histogram to the scenario. On that homework question, I think one of them is fairly obvious, and the other 2 are actually kind of tricky. On a test, I wouldn't put a question that vague, because you really, as long as you make a good case, you could. There's 2 of them there that you could argue for one of the situations. So on a test, everything will be very clear. All right. Let's then talk about spread. So for the same reason that we have 2 measures of center, one for symmetric data and one for skewed data, we also have 2 measures of spread. So for symmetric data, corresponding to the mean as our measure of center, what is our measure of spread? The standard deviation. Now I'm writing this up here, but don't get scared. That doesn't mean you need it on the test. I've already told you you will not need to compute a standard deviation on the exam. But it doesn't hurt to have the formula if you suddenly forget what a standard deviation means, and you can understand this formula. It should tell you all you need to know. But more importantly, intuitively, what does it mean? The standard deviation.
How far from the mean?
Yes. It's on average how far a data value is from the average. So think of it as average distance from the average. I have this data set here. It has some average. Every point is some distance from that average. I average all those distances. That's my standard deviation. What was our measure of spread then for skewed data? Much like the mean is susceptible to extreme values, so is the standard deviation. It does have the mean in its formula after all. So when I have skewed data, I don't use the standard deviation. Instead, I use, anyone remember?
Yeah, the
Not quite. The IQR. This is the interquartile range. It's called that because it's the 3rd quartile minus the 1st quartile. Q3 minus Q1, yes.
So we use standard deviation to symmetrical.
Yes, if the data is symmetric, you use the mean as your measure of center and the standard deviation as your measure of spread. If the data is skewed, either left or right, you use the median as your measure of center and the IQR as your measure of spread. So let's find the IQR of the same data set here. Q3, the 75th percentile or 3rd quartile,
60.
it's just the midpoint of everything above the median. So this is 60. Q1 is the midpoint of everything less than the median. I have 3 numbers here. 20 is the middle. So I have 60 minus 20. Again, you need to put the data in order before computing the IQR. Like the median, it's an order statistic. Yes?
How do you know what's the standard deviation? How do you know what's IQR?
Standard deviation when you have symmetric data. IQR when you have skewed data.
Thank you.
Remember, the two things that need to be put in order first go together. The IQR and the median go together.
So an example would be if there's an outlier, you're going to use IQR.
If there's an outlier, so in reality, it's a bit of a judgment call if something's skewed or symmetric. If I have something that's like this, and then one guy out here, yeah, that has an outlier, so technically it's skewed right, but that's only one data point in an otherwise very symmetric distribution. So in real life, it can be a bit of a judgment call. But in general, to answer your question, yes.
Would you go with something like that?
No, definitely.
Do we usually use the SD or do we use the symbol for standard deviation? Or it doesn't matter?
So the symbols, remember in chapter 4 when we did linear regression, a sample standard deviation is a lowercase s, and then you can put what variable you're talking about there. A population standard deviation is that symbol. On my exams, I don't use symbols because I don't want this class to be all about remembering what a symbol stands for. So I'll write out the word standard deviation, mean, median, all the things like that. So everything will be in plain English. Okay. So after we learn standard deviation,
What is spread?
spread. Spread is, so let's do a spread literally means how spread out the data is. If I have one histogram that's like this, and then another one that's like this, clearly one is more spread out, right? This one would have a higher spread. Think of it the same way we define the standard deviation, the average distance from the middle. There's a reason that's a measure of spread. The example we saw in lecture was this one has all its data here in the middle. That's the tallest bar. So the average distance from the middle is going to be really low on this histogram. Here the data, same middle as that one, let's say. The data is clustered far away from the middle. These tall bars are at the extremes. So I'm going to have a lot of high distances from the center, and when I take the average of those, I'm going to get a high standard deviation. So spread is just, on average, how far from the middle is the data. Does that answer your question?
So would the first one have more spread to it then?
This one has a high spread, and this one has a low spread, because here the data is clustered in the middle, so it's not very spread out at all. Here the data is clustered far from the middle, so it's quite spread out.
Non-symmetric.
Sorry?
Non-symmetric.
These would both be symmetric, yes. So after we learned standard deviation, we started counting by standard deviations. We called that a z-score. Our formula for z-score was x, whatever value we're computing the z-score for, minus the mean of the population divided by the standard deviation. Write down the formula on your cheat sheet, but more importantly, understand just what a z-score is intuitively. It's how many standard deviations away from the mean any given value is. We're just counting by standard deviations, whatever that standard deviation may be. So let's look at an example.
Could you explain that again?
Can you say the Z?
Yes, the z is how many standard deviations away from the mean a value is. So the standard deviation is, on average, how far from the mean a value is. The z-score is then how many of those standard deviations is any given value. Best done with a simple example here. The example I did in class, to refresh your memory what I'm talking about, IQs have a mean of 100 and a standard deviation of 15. Therefore, an IQ, which I might call X, my data value, of 130 is how many of these away from this?
4.
2. 2 times 15 is 30. 100 plus 30 gives me 130. So the z-score for this IQ equals positive 2. Just counting how many standard deviations away from the mean it is.
Explain one more time, please.
Let's do the examples I have here, because we're going to do a lot of z-scores in the examples, and that should clear it up. What we did with the z-score was,
Sorry, what's the X equation given?
X is our observed value. So for what I did over there, the X would be the 130.
And it's given.
Yes, the mean and the standard deviation have to be given for you to be able to compute a z-score. And you also need to be given the observed value. Let's say so we're talking about the empirical rule, which tells us probabilities based off the z-scores. From, maybe I should make this bigger. From -1 to +1, these are z-scores here. So what's the z-score for the mean itself?
0.
0. No matter what that mean is, the mean is always 0 away from itself. 1 standard deviation below the mean, 1 standard deviation above the mean. In that range, I have 68% of my data. And the range from -2, so 2 standard deviations below the mean, to 2 standard deviations above the mean, I have 95% of the data. And from -3 to +3, I have virtually all of it, 99.7. I'll give you a big hint right now. I don't like working with -3 and +3 because 99.7 is not a very friendly number to do math with in your head.
Thank you.
So what do we do with the 1s and 2s then? Let's say, looking at minutes commuted to work. The mean is 25 minutes. This is national. Standard deviation of 5 minutes. What is the probability that your commute to work in minutes is between 15 and 35? So this is exactly the kind of question you'll see on the midterm regarding the empirical rule.
That was provided to us, or?
I'm sorry?
Like the articles with both of
These will be provided. I mean, they'll be provided in a sentence. Yeah, I'll say the mean is blah, blah, blah. Yeah. Yeah, you need to be given the mean and standard deviation. There's no way to find those unless you're given the whole data set, which I wouldn't do. What's my first step in finding this probability?
You gotta find the distance away.
Exactly. The empirical rule is written in z-scores here, not in minutes commuted to work. So I need to first convert all this to z-scores. Again, a z-score is how many standard deviations away from the mean a value is. So now I replace minutes with z, and I find the z-score of 15. How many of these below this is 15?
2.
2. -2.
them.
Remember, the sign of the z-score gives me the direction. If it's negative, it's below average. If it's positive, it's above average. You can just follow the formula. X is 15 minus the mean of 25 divided by the standard deviation of 5 gives me negative 10 over 5,
It's 5%.
negative 2. Also just see that 2 of these is 10. 25 minus 10 is the 15 I was looking for. So 2 of these below the average. What about this one, 35? Positive 2. If I replace this as a 35, I'll have positive 10. Divided by 5 is positive 2. All right, now we've converted our data to z-scores. Now we need to use the empirical rule to find that probability. This is an easy one. What's this one? 95. The rule just gave us this one, from negative 2 to positive 2. Yes?
Will that be on the map?
Good question. This, the empirical rule, I will not print on the test. So make sure you copy this down right now and have it on your cheat sheet. Let's try another example.
Wait, so for that answer, it's just 95%?
95%.
Being able to get in between that range.
This would mean, let's say I randomly picked one of you from this classroom. The probability that your commute is somewhere between 15 and 35 is 95% chance. Yes.
Would you please explain how do you get to 15, 35 as 35 as your probability?
How do I get these numbers?
Yes.
These numbers are just part of the question.
Okay, they are part.
Yeah, these would have to be included in the problem.
Because you just said that the mean and the standard deviation would be in the question.
Yeah, all this has to be, this is all your given information. I need to give you the mean, I need to give you the standard deviation, and then I need to give you a question to answer.
Right.
And then you'll convert
Plug
it.
Makes sense.
Let's look at the probability that minutes commuted is between 25 and 35.
Are you doing it again?
Sorry?
Are you doing it again?
Different problem. This one was 15 to 35.
Oh,
Now I'm doing 25 to 35.
The same mean.
With the same problem. Same mean, same standard deviation. So what's the z-score of this one?
0.
0. It is the mean, right? 35, we already found the z-score of that, positive 2. Well, this one's not given as easily by the empirical rule, but still fairly easy. What is this one?
it's
35.
47.5.
95
minus
Yeah, he got it.
47.5.
It's 95. It's half. From negative 2 to positive 2 is 95. Then from 0 to positive 2 is just half of that.
Yeah.
Notice that's only true around 0. The distance from negative 2 to 0 and from negative 2 to negative 1 is not half of negative 2 to 0. That's only true if you're splitting it at 0. Does that make sense what I just said?
Mhm.
That's because this thing is only symmetric around 0.
Why is it 95 minus 68?
No.
It's from 0 to positive 2. From negative 2 to positive 2 is 95. 0 to positive 2 is half of that. So it's 95 divided by 2.
0 and positive 2 we got from where?
0 and positive 2 are our z-scores. So the z-score for 25, I'd have 25 minus the mean, which is 25, divided by the standard deviation, which is 5. 0 over 5 is 0. Let's do one more then.
I have a question.
Yeah.
25 and 35, so why is it 25 minus 25? Who's 25?
This 25 in this case is both the given observed value and also the mean that you were given.
Oh, we're doing it off that.
Yeah, we're using the same data. Let's look at the probability. So your commute is between 20 and 35 minutes. So hopefully now you remember the first step, z-score.
-1.
The The z-score is -1. 20 is 5 below 25, so it's only one of these below, so it's -1.
+2.
35 we've been using is +2. Right, -1 to +2.
So
Well, we already got part of it. We know from 0 to +2 was 47.5. What piece am I missing there?
-1.
-1 to 0.
-1 to 0. This piece here. What is -1 to 0? I'm sorry?
34.
Exactly, 34. Half of 68. Do you guys see where that came from? It was the same logic that we used to find the 47.5. If from -1 to +1 is 68, then from -1 to 0 is just half of that 68, 34. So here I'd have 34 plus 47.5, 81.5. So we've done 3 examples that range from the very first one I did, which was just 95%, as easy as they can possibly be, to this one, where I had to find 2 things that were not on there and add them together. That's really as tough as they can get. On the test, I'm going to put it much closer to the easy side. But you still need to know how to read this empirical rule. Questions on our examples there? Okay. What if I just gave you a z-score and asked you to find the minutes? So here I gave you minutes, then you found z-scores and went to probability. What if I said z equals +1 for some commuter? How many minutes is his commute?
34%.
34% is a percent, not minutes. I said how many minutes?
30 minutes.
It would be 30. Remember, +1 means 1 standard deviation above the mean.
25.
One of these above this, 25 plus 5 is 30. If you don't want to think that much, remember your formula. Z equals x minus mu over sigma. I just gave z as +1 equals x, what we're trying to solve for, the minutes commuted, minus the mean of 25 divided by the standard deviation of 5. Solve for x. I get x equals 1 times 5 plus 25 is 30.
So that would be a question, just figure out like, find z.
Yeah.
Okay, that's it, okay.
Well, here the question wasn't find z. Here the question was, here is z, find x.
But find it, okay.
With the same median and standard deviation, using those.
Yeah, what I did here, I'm still
Okay.
working off this same data.
You just put
On a
plus
test,
1.
I'm likely to do this. I'm not that creative to be coming up with new. I had to Google just to come up with minutes commuted to work. So on the test, I'll have like for problems 10 through 13, use this information, something like that. Yes. This picture here, yeah, is all you need, and the knowledge to how to use it. All right. Let's move on to chapter 4.
So we're still in chapter 1.
No, we just finished chapter 3. We're not still in chapter 1.
Now, on the cheat sheet, if I wanted to use, for example, what we just did on the board, am I able to have that on the cheat sheet?
Yes, so guys, let me get your attention, please. Thank you. The question was, can you put an example on your cheat sheet? The answer is yes. There's no limitation to what you can put on the cheat sheet other than its size. But you can put solve problems, anything you want. You can type it real tiny. I see people do that every quarter. It's not advantageous. Remember, the more stuff you have on there, the more stuff you have to look through. But if you want to, go ahead. 8.5 by 11. Normal piece of paper, both sides. Anything you want. Okay. So in chapter 4, we saw a new type of graph, or a new name for an old type of graph, the scatter plot. The scatter plot is just the XY coordinate system that you've seen before, hopefully. Every point, so now our data will appear as points on this scatter plot. Every point has two coordinates, x and y. Those would be two values. So we did a lot of examples with height and weight. And the goal of linear regression is to observe the trend in this data. This is, remember, we call this a positive trend. As x increases, y is increasing. And our goal is to find the best fitting line that in some sense fits this data. We'll talk about that. So our x variable, we often call the explanatory variable because we want to use the x variable to explain y's behavior. So what I have here is square feet, SQFT, and we want to use that to try and predict home price, the price of a house based on square footage. You need to be given mean and standard deviation for each of these. So price, my y variable, the mean is y bar. Let's say I had a mean of $500,000. The standard deviation of my y variable, let's say, is $100,000. The average square foot, x bar, say is 1,500 square feet. And the standard deviation of square feet is 500. This all has to be given in the question, and it will be. There's 5 pieces of information you need. This tells me all about x. This tells me all about y. Does anyone remember what tells me about the relationship between x and y?
Point.
Sorry?
Point.
That's where if it's 0.97
Positive.
Yes, that has a name though, that quantity. You said it earlier. Another word for association. What would do?
Correlation.
Correlation. We denote the correlation as a lowercase r. It goes from -1 to +1. The sign is giving me the direction. So a -1 would be a perfect downward sloping line, like this. The data is in a perfectly straight line because it's a 1, downward sloping because it's negative. The other extreme is the opposite. Perfectly straight line sloping upward. Again, straight line because it's a 1, upward because it's positive. In the middle, at 0 correlation, that's where we see just a random scatter. I'm not drawing the axes here. Maybe I should be. Correlation of 0 means y's behavior is too unpredictable, so we cannot fit any kind of model that predicts y's behavior based on x. In reality, we see things like this. So let's say this is some data set, correlation maybe 0.4. This one's more tightly packed, maybe 0.8. And then, just for completeness, the extreme end. So the higher the absolute value of the correlation gets, the more tightly packed our data is, this data cloud. So let's say our correlation between square footage and price of the home is 0.75. All right. Our goal is to find the equation of the line that best fits the data. We write it as y hat, meaning predicted y, equals a plus bx, where a we call the intercept, and b we call the slope. Now the definition of this best fitting line, and I'm not going to ask questions about this on an exam, You need to know how to find the line, but the details are best left to another class. Remember, it was the best fitting line was the line that minimized the squared residuals. So for any point, there's some distance from the line, which is our predicted value at that x, and then the actual. The distance between them is just how wrong our line was. We call that the residual. If I take all the residuals and I square them and add them up, I'll have what we call the sum of squared residuals. And there is some line that will give me the lowest possible sum of squared residuals. And we define that to be the best fitting line. So it's the line that's somehow simultaneously closest to all the points. We don't really worry about finding it that way. We have formulas for our slope and intercept, which are much easier to work with. Our formula for slope, b, the correlation, times the standard deviation of y, divided by the standard deviation of x. We always want to find the slope first. The intercept, A, is y bar minus b x bar. So the average y minus the slope you just computed times the average of x. Remember, sorry?
Is the residual given?
No, the residual is not necessarily given, but you can use the line to make a prediction, and then if I give you the actual, you can compute the residual, which we'll do an example of very soon. All right, so let's find the slope. Again, those 5 values will be given. Let's find the slope. We have 0.75 correlation. Standard deviation of y, oh, this is what I was going to say. We're always predicting y from x. So the question would say something like, find the linear regression model predicting the price of the home from its square footage. On the test, I will actually say, though, in parentheses, this is the y variable, this is the x variable. Standard deviation of y then is 100,000. Standard deviation of x is 500. We have a slope of 150. Let's find the intercept. The average y was $500,000. Minus the slope we just computed, 150, times 1,500, the average of x. Give me 275,000. Do you have a question?
Yeah, was the article 0.75 given?
Yes. 5 pieces of information must and will be given. The average of both values, the standard deviation of both values, and the correlation between the 2 values. Those 5 pieces will always be given. So I have my slope and my intercept, so we can put it together. Y hat, we know y is just price, so I'm going to have predicted price equals my intercept, 275,000, plus my slope, times my x variable, square footage. So this is the best fitting line, the linear regression model, to predict price from square footage. What do we use the line for? What's the whole purpose of doing this?
To see if y increases.
It is to generally just model the relationship between
If you
x and y. Yes.
if you over or under the residual, if you overestimated it or underestimated it?
Estimated. That's the purpose of this line, to make estimates, or in other words, predictions. So let's say I wanted to use this line then to predict the price of some house that isn't on the market yet, but I know it's square footage. So let's say the square footage of the house I want to predict for is 2,000 square feet. It's 2,000 square feet. What is the price? So how do we find that once we have the line?
You multiply 150 times 2,000.
Right, we just plug it in for that variable. So I plug in 2,000 for square feet.
Where do you get 2,000?
The 2,000 had to be given. I'm asking you to predict the price of a home that is 2,000 square feet. I could have just as easily asked you 4,000 square feet or something, as long as we're not extrapolating. But you don't need to worry about it. I'm not going to put any extrapolation stuff on the test. Yes.
Where do you get the price formula?
Yeah, where did that come from?
This here,
The price formula?
I don't know what you mean by the price formula.
Where did that arrangement came from?
This-
It's the intercept.
This formula right here, is that what you're talking about? This was, let me put this back.
Okay.
This came from what we did over here. The slope we solved to be 150, that's where that came from. The intercept we solved to be 275,000, that's where that came from. Remember, this here was our goal, and this is the same as this, except we plugged in our values. Does that answer your question?
With the question will always, it will ask for an answer for X, to solve for X. Meaning like,
Solve for X?
yeah, meaning like, so we wouldn't have like to flip it, it wouldn't be something where we would guess that. Would you do something where if it's square feet, what would be the price? Do you know what I mean? Like for
Well, that's what I'm doing here. I'll always give you an X and ask you for a Y.
Okay.
I'm not going to ask you for a Y. I'm
That's
not going
right.
to give you a Y and ask for an X. No, I would never do that. That's actually, it's actually invalid. You would think that you could just solve for square foot in this line and it would come out true. It won't. And the reason for that is essentially if you did that, you'd be taking the reciprocal of the slope. That doesn't work. It's just flipping this. It gives you Sx over Sy, which would be fine, but we still have R in the numerator, so you actually cannot just solve for X. Good question. Okay, so let's make our prediction for this house that is 2,000 square feet. You just plug it in for the square foot variable. I get a predicted
75,000.
575,000. Thank you. Again, that's predicted. That's what the little triangle over price means. Now this part will have to be given. It will be a question. Let's say I go out and I find a house that is exactly 2,000 square feet. And I look on Klein and it is priced at exactly 500,000, 500,000. So this is what the house is actually priced at. This is what I predicted it would be priced at. A residual. So first off, did my model over or underestimate? It overestimated. We define the residual as actual minus predicted. So I'd have 500,000 minus 575,000,
75,000.
or a negative 75,000. Now you don't need a residual to know that this model overestimated. 575 is more than 500,000, so the model overestimated. But notice that any time our model overestimates, we're going to get a negative residual. And any time our model underestimates, we're going to get a positive residual. So if all you know is the residual, that tells you whether you overestimated or underestimated. Questions?
Yeah, positive residual is underestimated.
Let me get this. Yes. What's that?
Underestimated.
Yeah.
Positive residual is under. Notice it's kind of reverse. So
Right.
keep that in mind. Positive residual, underestimated. Negative residual, overestimated.
Okay, so on practice problems, you gave us predict the regression line, and then you asked us to interpret the slope and intercept in context. Are you gonna ask us the same thing in?
Yes.
exam?
So let's do that now. Let's put this back as square feet, our regression line. Our slope, remember the slope is the one being multiplied by our x variable. What does the slope tell me? The slope is the rate of change. It tells me the rate of change of y as x changes. Remember from high school, rise over run. If square feet were to increase by 1 square foot, what do I expect to happen to the price of that home?
Plus 100%.
is being multiplied by 150, so I do expect that to increase by 1 times 150, which is 150. Which I guess would be dollars here, price. So a 1 unit increase in x is associated with a slope increase in y. Is a general way to word that. What about the intercept? How do we interpret that? You always plug in 0 for your x variable. So this would mean that I predict a home that has 0 square feet will be priced at $275,000. We always start that way to interpret the intercept. Plug in x equals 0. And then we ask ourselves, does it make sense? 0 square feet priced at $275,000?
No.
Not really, unless it's like an empty plot of land. Certainly land has value. On the exam, I'm not going to put a question like that. I'm not going to ask you, does it have a real world interpretation? That can be a little subjective. And that's, if I have one goal on exams, it's to not be subjective. Yes.
I'm taking from the home or the practice problems from chapter 4. Are you going to give us a problem where the example that I had a problem with was find the linear regression equation for predicting the kindergarten's weight from height. So we're going to have that on the test where we have to decide where weight and height will be on X or Y?
Well, again, on the
Just in terms
exam,
of how the question is being asked. Do you know what I mean?
you will have to find a linear regression model. You will not have to figure out on your own which is y and which is x.
Okay.
Because on the test, I will put parentheses y, parentheses x when I name the variables. Other questions there? All right, the last thing we talked about in linear regression was this capital R squared. We call it the coefficient of determination.
It's called the what? Coefficient?
Coefficient of determination. Which, to be honest, I don't even know what that name means for a determination, but it's giving us the percent, so the textbook definition, the percent of the variability in y that's explained by x. Remember, we called x the explanatory variable. We want to explain y's behavior using x. So the higher this percentage, the better job the model does at actually explaining y's behavior. So in this case, so the coefficient of determination is just the square of the correlation. So 0.75 squared gives me 56.25%. That means 56% of the variation in home prices can be explained just by looking at the square footage of the home. That means there's about 44% that remains unexplained, right? That's always going to be the case. The only time we'd ever have x completely explaining y is if the data happen to lie in a perfectly straight line where nothing was random and everything was very predictable. So what other factors go into a home's price?
What's inside the home?
When it was built.
How old it is, what's inside, if it's coming furnished, the location primarily is probably the biggest determinant. Certainly a massive house in Montana would probably still cost you less than an apartment in New York. So there are other factors, but 56% of it is its square footage, according to this model. Think back to in class we looked at height and weight. If I have just a list of weights, I have heavy people, medium people, light people, and I don't know why there's such a variety of weights. Then I look at height data and I see this positive trend, find my line. I go, okay, well some people are heavier than others because some people are taller than others. That's what the line's really telling me with its positive slope. So part of the picture of weight is explained by height, but not all of it. Part of the picture of a home's price is explained by its square footage, but not all of it. That's exactly what R squared is giving me. What percent of the variation in y is explained by x.
So we're supposed to find a valid interpretation of a value. For example, in our practice problems, where we did the math SAT scores, it was B, where we said it was. So we look at the variable. What is right there because it was the square foot? Where we look the interpretation was the square foot, or what would it?
Yeah, I mean, you want to plug in actual words. You could call it X and Y, but why not be more specific if you can? It's still true to say 56% of the Y variable can be explained by X, but if I know that Y is price and X is square foot,
So one more time, what does the R squared tell us about the data? Tells us what?
it tells me, so Y, whatever my Y variable is, in this case a home's price, is going to have a lot of factors that go into its value. We've already talked about a few: a home's price, location, square footage, what's in the house, a lot of different factors of what goes into a home's price. Square footage is one of them. How big of a factor is it? It's 56.25% of all factors. So it's a really big factor. Other questions?
So the R square is pretty much the portion explained.
Yes. Yes, that's exactly what it is. It's the proportion or percentage of the variability in Y explained by X. Yes? I can't hear you. I'm so sorry. One more time. The little r is correlation, not residual. Residual. This is what a residual is. Actual minus predicted. It's the error in our model. And then little r stands for the correlation, not residual. Questions there? All right, it's 7:33. Let's meet back here at 7:43, and we'll finish with chapter 5, our last chapter.